Okay, hello everyone. Hope everyone's doing fine and staying healthy. So let's continue our course, ODE course. We're going to finish off chapter 3 by looking at autonomous second order differential equations. So remember, an autonomous equation is one in which the independent variable doesn't appear. So something like x double prime plus x equals 0. We're actually not going to spend that much time on it because we're quickly going to see that the way that we handle these equations, this second order differential equation is to consider it as a pair of first order equations. And then that's going to be a major topic we're going to look at later. We are going to have a look at a thing called the phase plane, which we're going to do in the next module. But first, we're going to have a look at numerical methods. And firstly, because it's nice to know how the computer actually goes about solving the differential equations that you see, but also it kind of points out what I was saying about the way to treat these second order equations is just as a pair of first order equations, and that the methods that we then used for numerical methods we used for first order equations work really well and basically the same for these equations right here. So remember, a second order autonomous equation is going to look like so x double prime is some function of x and its derivative x prime. And so the way we set up the initial value problem, notice that we have x t naught equals x naught and x prime of t naught is y naught. Before, remember, we had it as v naught because then we were thinking of x prime as some kind of velocity. Here, this is foreshadowing the fact that we're going to be thinking of this as a pair of dependent variables, x and y. And so the first thing we need to do the theory, of course, is an existence and uniqueness theorem. And for second order nonlinear equations, it's very much like the first order nonlinear theorem that we saw, and not at all like the second order linear equation. So remember, for the second order linear equation, the existence and uniqueness was basically for all t, as long as the functions were continuous themselves. Here, if we've got x double prime is a function of x and x prime, if we look at that function f, and if the partial derivatives with respect to x and with respect to x prime are both continuous in some region containing our initial values, x naught, y naught, then there exists a unique solution. However, that solution is only guaranteed to be in some interval, in some neighborhood of t naught. So it exists some epsilon such that the solution exists for t naught minus epsilon to t naught plus epsilon. Okay, so since solutions exist, this is basically the whole reason why Euler's method is guaranteed to work. And so, as I said, the basic trick is to turn a second order ODE into a pair of first order ODEs. And in general, that can be done for an nth order ODE. You turn it into a system of n first order ODEs. And the way that you do that, we'll see how we do it for second order, and it's exactly the same what you do for nth order. And so since it's a first order ODE, we can use the methods that we've used before. So we could use it for all the methods, but we're only going to look at Euler's method because really I think this is a method that like every educated math person should know, and it's something you should be able to do by hand without very much problem. Whereas with the other methods, you have to actually memorize things. So, firstly, given our IVP, we converted into a pair of first order equations by letting y be the derivative of x. So that means x prime equals y, and y prime is that function of x and y now. Okay, and so it's the part. So the whole thing works as long as the partial derivatives of f with respect to x and y are continuous. Okay, so we choose a small step size. You know, we're going from t0 to t max. So we cut up that interval into n sub-intervals. And so we want that to be a nice small step size. And we know the smaller step size, the less error we'll have and the better approximation we'll get. And then we just do the Euler computations, right? For j equals 0, 1 through to n minus 1. We let the new x be the old x plus its derivative times the step size. The derivative, of course, being just y. The new y is the old y plus its derivative times the step size. And its derivative, of course, is f of xy. And then the new time is the old time plus the step size. Very easy to implement. And so if you go ahead and plot those points tx and connect with straight lines, you'll get a nice piecewise linear approximation to your solution x. And of course, this is how the computer actually draw solutions to differential equations. It doesn't use Euler's method, it'll use the Runge-Kutta method, right? Euler method, we know, is pretty dodgy because it's only a first order method, meaning you have to do a lot of work to get good answers. So if you double the accuracy, you need to double the number of points in your grid. As I said, if you're going to implement anything by computer, use the Runge-Kutta. If you're going to do things by hand, use Euler, I guess. Runge-Kutta is a fourth order method, which means that if you double the number of points in your grid, you get 16 times more accuracy. And so usually the way you use these methods is, you choose a nice small step size, look at the answer you get, then you look at a smaller step size, you might say halve it, look at the answer you get, and you see whether the answers are stabilized or not. So if the numbers haven't changed at all, you've got stabilization of your answer, and so you know you've got a good answer. So if you go to the Excel file that I did for the module, it approximates the IVP x double prime plus x equals 0, which we know the solution of that is going to be sine or cosine. And if we have the initial conditions, x naught equals 0 and x prime naught equals 1, then that, of course, is sine of t. Okay, so have a look and play around with that. And so a question for you is, look at the error for computing x of pi on 2. X of pi on 2, of course, should be 1. So I've done there with 10 steps and 100 steps. So how would you predict the error to change? How does it actually change? And what n would you need to use to get an answer correct to 5 decimal places? So this is a question that I want you to just write in an email to me by next Wednesday, this Wednesday. This is just a thing to show me that you have completed this module. And as well, there will be a homework question, and that will be due in 2 weeks, because next week we have the fun of doing an exam. So that's going to be fun and games. Okay, so this is a nice, I thought this is a nice light module to start with, and on Wednesday I'll publish the next one, and also on Wednesday, so next Wednesday I expect the homework that was given before the break. In a separate email, give me the answer to this question, and I'll contact you. Oh, I'm going to be, I use Zoom to make this, so I think we're going to be using Zoom for office hours. So talk to me sometime. Okay. Have a good time.